Alrighty, 4.3, Introduction to Composite Functions. So first thing we're looking at is trying to figure out what is a composition. Well, we got Clyde, your composition on my dog is exactly the same as your brother's. Did you copy this? No, it's the same dog. I know that sounds like some of the excuses that you guys would use, but I don't think that's exactly the composition we're talking about. So let's look at the mathematical definition of what a composition is, or a composite of functions. Think of it as two machines. We've got machine 1, which is the first function. So every function is a machine. And we've got a second function, which is machine B. Okay, so this could be an f at x, and this could be a g at x equation. So two different functions. I like to think of a composition as kind of like this here. I'll do another quick drawing for you. So we've got, let's see, the first machine that we have, let's say you've got a hunk of steak. And you take that steak and you throw it into a meat grinder. It goes in and gets all churned up and out that back end. So our input was some steak. Hopefully it was still good steak and it didn't have E. coli all over it. Gets thrown in, gets all churned up, and out pops at the bottom end. We've got our output, and that would be ground beef. Oh, ground, maybe these are ground beef. Now, we've got this ground beef sitting there. Let's say, hey, we want to make hamburger patties. So now we're going to take that ground beef, which was the output of the first machine, and we're going to throw it into the second machine here. The ground beef now becomes the input of the second machine, and maybe this is a patty maker, and it pounds it down, bum, 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 and out the end of that one, we now get another output, which is patties. You get a hamburger patty. That's an example of what we're doing here with compositions. We're taking the input of one machine, and the output is going to become the input of the next one. For instance, what's the output from machine B for each input in machine A? If we throw a 3 in, what's going to pop out the end here? So work it through first. The 3 goes into 2x plus 3, so we get 2 times 3 plus 3, which gives us 6 plus 3, which is 9. That 9 now becomes the output of machine A goes to the input of machine B. So now we take that into the second machine and say 1 over x plus 5, so 1 over 9 plus 5, which gives us 1 over 14. And then we do the same thing with the 0, starts right through the beginning, and the negative 2. All right, here's another example of where we would use compositions. For a vehicle, the cost of gasoline, C dollars, is a function of the amount used, V liters. This can be written as a function, C cost of V of the liters. The amount of fuel used, V, is a function of the distance that you've driven in kilometers. We can write a function with that, where V is a function of D. Since C is a function of V, and V is a function of D, C can be written as a function of D. So it looks like this. So what we've got there with this new fancy crazy thing is just saying the cost of gasoline with respect to the distance you've gone. It'll become a lot clearer when we actually look at equations and numbers. This leads us into notation, though, for compositions. A composition has two different notations that we can use. The first one, which is the easier one to use, and the second one, which is more commonly given. Okay. And what you read them as is f of g at x. In other words, we're taking one function and stuffing it into the other function. Okay, so we can also get the answers from an arrow diagram. So if we're looking for f of g at negative 1, start with the inside first. We're always going to start here. Start inside, work outward. Start in the inside, work out. So we're going to, first of all, just pay attention to what's g at negative 1. So let's go to this first one. The first one is talking about g, and we need to find where is g at negative 1. So x of negative 1, go across, and that gives us 2. So we can see that g at negative 1 is 2. At this point, we're saying g at negative 1 was 2, so we're looking for f of 2. We go into the second equation and find where f was 2. Oh, there it is. And slide it across and over, and we've got 3. So we can say f of 2 is 3. So then the whole thing together, our original question, f of g at negative 1 is equal to 3. And showing where we started, we went from here to there, to there, to there. Let's look at this graphically. We can take those two arrow diagrams and turn them into f was actually a line and g was a parabola. We graph those on there. Now, the thing that you're going to want to do whenever you get one of these is do the next step yourself. You want to always graph y equals x. The reason for that is it helps with each step. So first thing you want to do, draw a vertical line through x equals negative 1, up to there. Find the intersection with g, because g was the inside function. We start on the inside. And we find where does it intersect. And it intersects right here, at negative 1, comma 2. Next step. Go with a horizontal line now across, and find the point on y equals x. That's why we drew y equals x, so we could find out where it's on that line. 2, comma 2. And then from there, we're going to draw a vertical line going to the f, or the outside function, and find the point there, 2, comma 3. The y value of that is going to give us our answer, the 3. What we've got here is called a web graph. All right, using the information from their example 1, we're going to continue on with it. From a table of values, we want to know g of f at 2. Start with the inside function. We're going to start at f at 2. So find an x value of 2. That's where we're starting, an x value of 2. Find that right here, and go across and find the value. It's equal to 0. Now we continue along with that. So we say f at 2 equals 0. And we continue along with that, and that becomes the new input, the 0. And go across to 1. So now we're saying g at f at 2 is equal to g of f at 2 was 0, so g of 0, which is equal to 1. Hey, but I don't need 2 different functions to be able to do this. I can stuff one into itself. Lots of fun there. That's a party trick in itself. G at 2, we're going to start there. So go to your g equation. Find when x equals 2. Oh, x equals 2 here. Find the value. So now we're saying that g at 2 is equal to negative 1. Continue with that. Take your negative 1, and we need to put it back in for the x. But we're putting it back into itself, back into the g. Which means we're going g at 2 is equal to g at negative 1. All I'm doing is I'm substituting here. I'm saying okay, g at 2 is equal to negative 1, so I just put that right into there. It's a substitution game here. And now I've come back and said at negative 1, it's equal to 2. Don't think, though, that just because I started with a 2 and I ended with a 2 when I put it into itself, that's always going to be true. That's a coincidence on this graph. It's not always going to happen. Now, hey, you do this. I want you to do the thinking on this one. Why couldn't we find what f of f at negative 2 is equal to? Why don't you try that one out? Come up with a reason why this won't work for us on this occasion. Make sure that you have done the thinking on that thing further. It is extremely important that you make that connection yourself. All right, before I get into doing our example 2, we're going to look at Buddy here. He's going to explain their example 2 for you and their process.
Part A. Given the graphs of y equals f at x and y equals g at x, determine the value of f at g at negative 2. I'm going to start by drawing the line y equals x. I'm looking for the value of f at g at negative 2, so I can start by finding the value of g at negative 2. I'll draw the line x equals negative 2 from the x-axis up to the graph of y equals g at x. The line intersects the graph at p negative 2, 8, so g at negative 2 equals 8. This means that the value of f at g at negative 2 is the same as the value of f at 8. I can find the value of f at 8 by drawing a horizontal line from p to the graph of y equals x. The line intersects the graph at q. Now, I'll draw a vertical line from q to the graph of y equals f at x. The line intersects the graph at r, 8, 3. So, the value of f at 8 is 3, which means that the value of f at g at negative 2 is 3. Part B. Given the graphs of y equals f at x and y equals g at x, determine the value of g at f at 3. Just like in Part A, I'm going to start by drawing the line y equals x. Now, I'll draw the line x equals 3 from the x-axis up to the graph of y equals f at x. The line intersects the graph at S. Now, I'll draw a horizontal line from S to the graph of y equals x. The line intersects the graph at T. Finally, I'll draw a vertical line from T to the graph of y equals g at x. The line intersects the graph at U, 2, 0. So, the value of g at f at 3 is 0.
Fancy stuff, fancy stuff. Here we go. It's our turn to try it out. Okay, so first thing you want to do when you're doing graphically your compositions is to draw your line y equals x. Okay, through 0 and 0, 1, 1, 2, 2, 3, 3, 4, 4. So right through there, making it beautifully straight. Oh, nice. Look at that. All right, now let's go through. Start with your inside. G at 2. So we're going to go to our graph, find our 2. Okay, so we start there. Oh, there we go. It's right on the axis. So then from there we go up vertical to the line y equals x, horizontal across to the, go vertical. So from here, go horizontal first. That's what I meant to say. To here, it's now at 0, 0, then up to your point there, which was right here at 0, 1. That's the value we're looking for right there. So again, from your original point of x of 2 intersects the g there, go horizontal to the green line, which is your y equals x, then go vertical. Horizontal, then vertical, alphabetical order. Might be worth drawing their arrow lines so you've got your pathway that you follow. Okay, so f of g at 2 equals 1. Let's do the next one. We're starting on the inside. F at -1. So find your -1, which is right here. Nice that they're giving you another one at the axes. Bring it in to our green line, which is at your origin, and then vertical to the other line, which takes us to 4. Let's draw the arrows on this one. Horizontal to the green line, then vertical to this point, which was 0, 4. We don't care about the first number, we only care about that second one, so we're saying it's equal to 4. Again, making the connections, thinking it further for yourself. Looking at that example, we know that the function is not defined at -2, because if you look at where it's sitting, -2 is beyond where it's defined. If we can't use -2 into the f, why are we still able to go and say g at -2 and then find the f of g at -2? Write that one down. Hey, so nice to be able to use a graph, but you're not always going to have a graph. We got to be able to do it algebraically with the function notation as well. A couple of different ways of doing this. I'm going to try to show you both ways for the two different questions here. Always start on the inside. So first one, we're going to do it in 2 steps. I'm just going to pull out g at 9 and do that one separately. So again, function notation says wherever you see an x, put a 9. So we're using the g equation. And wherever you see an x, put a 9 there. So -2 times 9 plus 1 equals -18 plus 1 equals -17. And now, f at g at 9 is equal to f of, well, let's just substitute. The g at 9, that was -17. Substitute in. And now we're just saying, wherever you see an x in the f equation, put -17. So then, oops, I want the f there anymore. I want, oh, there's an x, so -17 squared plus 3 times -17. Plugging that into your calculator, but doom, 238. Look at that. And there's your answer to the whole thing. In the second one, I'm going to do it a little bit more in one step. I'm going to substitute straight into here. This is now saying g of f at 9 is equal to, well, I'm going to substitute this first part right here, straight into there. So I'm going to say g at, well, f at 9 is, oops, not that one. This is the f. Using the f equation. Substitute the 9 in there. So 9 squared plus 3 times 9. So all I did is substituted. Wherever I saw an x in the f, I put a 9. If you want, you can work this through to get a number, or you could take that straight through and put it straight into your g as such. Either way works. Most people like to evaluate it, so I'm going to evaluate this one. And that becomes 108, and you can substitute the 108 in for the g, which is negative 2 times 108 plus 1, which, hey, there we go, negative 215, good stuff. So notice here that if we looked at f of g at 9, and if we looked at g of f at 9, those two are not equal to each other because these two were not the same value. So the order does matter of which way you go. Now, we don't always need numbers to be able to work through with this. We can use x all the way through, and we can come up with a new equation. So instead of looking at just numbers and points, we're going to look at whole equations. And we're going to do the same way. Start with the inside and substitute the inside into the outside equation. I'm going to skip over the inverse part there, and I'm going to jump to number 4. I'll come back to the inverse right at the end. Okay, so let's practice this up. Let's get the new equation. So what this is saying is start with the inside equation, and I like to substitute that straight in. Put in the equation into there. So f at 2x plus 7. So now this just says wherever you see an x in the f equation, instead of the x, put 2x plus 7 into that spot. So then we've got 2 times, oh, there's an x, so I put 2x plus 7 in there, square it, plus 1. And then I work it through. 2 times, expand this. This is not 4x squared plus 49. That's a scourge on humanity. If you need to take it, bring it up on the side here, 2x plus 7 and 2x plus 7. You cannot distribute it in an exponent. You have to multiply it twice. So that gives us 4x squared plus 28x plus 49 and plus the 1 on the end. Distribute in the 2 and add the 1, 8x squared plus 56x plus 99. Boom. There's your new equation. Domain and range. This is a parabola. Hey, any parabola is XER. But the range, again, plug it into your calculator. Look at where the vertex is. Is it opening up? Is it opening down? This one's opening up, leading coefficient. And then we would look and say, from the graph, where's the vertex? Next one, g of f at x. Go in the other direction. Take your f of x and plug it in. Substitute that in. So we've got g of the f is 2x squared plus 1. Substitute, hey, into the g equation, wherever you see an x, put that. So 2 times, oh, there's an x, so 2x squared plus 1 plus 7. Distribute in the 2, add the 7, 4x squared plus 9. That's another parabola, so we know XER for our domain. Range, though, again, graph it. This one you should be able to see. My vertex is going to be at the 9 going up, so y greater than or equal to 9. Last one, stuff the g into itself. And we've got The G equation was, what was it, 2x plus 7. So wherever you see an x in the G equation, put 2x plus 7. So we start writing the G equation. Oh, there's an x, so I put this into its place. Two x plus 7, and keep finishing off G. So I'm going to kind of try to color coordinate this as much as possible here for you. There's the 2, there's the plus 7, and here's the x that I've replaced with 2x plus 7. Distribute into 2, add the 7 there, and we've got 4x plus 21. That's a line. So X-E-R, Y-E-R, done deal. Let me just color coordinate the first one again for you as well here. That's what I'm plugging into the X value. I'm going to have my 2 in front. I'm going to have my squared still there. And then I'm going to have, what color haven't I used it? Yellow, plus 1 on the end. All right, last part here, just going back to the inverse. This is a specialized case. The compositions can be used to determine if two equations are inverses of each other. Okay, so the inverse of this function here, again, switch your x and your y, resolve for y, you've got your new equation. The fancy thing about these is that when we're doing our inverse, we know that it's reflected about the line y equals x. Interesting. Very interesting. Watch this. If we do our f of g at x, plugging that through, we get x. If I go the other direction, g of f at x, plug the f into the g, I also get x. In essence, what's happening is that the two of those graphs, the composition, is collapsing in on the line y equals x. This is only going to be true if the two original were inverses of each other. And that is going to be one way of determining if two functions are inverses. Hey, finish off your 3 questions there for yourself. 1, 2, and 3. And I'm going to leave you with this final question. How do you spell composition with only 2 letters? I'll let you think about this one. I'll give you the answer, but I'll let you think about it. All right, see ya. Have a good one.